Imagine a world where fleets of mobile robots navigate warehouses with the precision of a well-choreographed dance, avoiding traffic jams and optimizing every movement. This is the future that Amazon is bringing to life with DeepFleet, a revolutionary suite of AI models designed to predict and enhance the coordination of vast robot fleets. Amazon has just deployed its 1 millionth robot across its global fulfillment and sortation centers, cementing its status as the world's leading operator of industrial mobile robotics. This monumental achievement coincides with the launch of DeepFleet, a groundbreaking suite of foundation models trained on billions of hours of real-world operational data. These models are set to optimize robot movements, reduce congestion, and boost overall efficiency by up to 10%. The rise of foundation models in robotics. Foundation models, which have gained popularity in language and vision AI, rely on massive datasets to learn general patterns that can be adapted to various tasks. Amazon is now applying this approach to robotics, where coordinating thousands of robots in dynamic warehouse environments demands predictive intelligence beyond traditional simulations. In fulfillment centers, robots transport inventory shelves to human workers, while in sortation facilities, they handle packages for delivery, with fleets numbering in the hundreds of thousands. Challenges like traffic jams and deadlocks can slow operations. DeepFleet addresses these issues by forecasting robot trajectories and interactions, enabling proactive planning. The models draw from diverse data across warehouse layouts, robot generations, and operational cycles, capturing emergent behaviors such as congestion waves. This data richness, spanning millions of robot hours, allows DeepFleet to generalize across scenarios, much like how large language models adapt to new queries. But here's where it gets controversial. Some experts argue that relying too heavily on predictive models could lead to over-optimization, potentially missing out on the flexibility needed for unexpected events. What do you think? Exploring the DeepFleet architectures, DeepFleet comprises 4 distinct architectures, models each with unique inductive biases to model multi-robot dynamics. Robot-centric RC model. This autoregressive transformer focuses on individual robots, using local neighborhood data, e.g., nearby robots, objects, and markers, to predict next actions. It processes asynchronous updates in pairs with a deterministic environment simulator for state evolution. With 97 million parameters, it excelled in evaluations, achieving the lowest errors in position and state predictions. Robot floor RF model. Employing cross-attention, this model integrates robot states with global floor features like vertices and edges. It decodes actions synchronously, balancing local interactions and warehouse-wide context. At 840 million parameters, it performs strongly on timing predictions. Image floor IF model. Treating the warehouse as a multi-channel image, this uses convolutional encoding for spatial features and transformers for temporal sequences. However, it underperformed, likely due to challenges in capturing pixel-level robot interactions at scale. And this is the part most people miss. The complexity of pixel-level interactions can be a double-edged sword, offering detailed insights but also introducing significant computational challenges. Graph floor, GF model. Combining graph neural networks with transformers, this represents the floor as a spatio-temporal graph. It handles global relationships efficiently, predicting actions and states with just 13 million parameters, making it computationally lean yet competitive. These designs vary in temporal, synchronous versus event-based, and spatial, local versus global approaches, allowing Amazon to test what best suits large-scale forecasting. The diversity in these models highlights Amazon's commitment to innovation, but it also raises questions about the scalability and practicality of these approaches in real-world scenarios. How do you think these models will fare in dynamic, unpredictable environments? Performance insights and scaling potential evaluations on held-out warehouse data used metrics like dynamic time warping DTW for trajectory accuracy, and congestion delay error, CDE for operational realism. The RC model led overall, with DTW scores of 8.68 for position and 0.11% CDE, while GF offered strong results at lower complexity. Scaling experiments confirmed that larger models and datasets reduce prediction losses, following patterns seen in other foundation models. For GF, extrapolations suggest a 1 billion parameter version trained on 6.6 million episodes could optimize compute effectively. This scalability is key, as Amazon's vast robot fleet provides an unmatched data advantage. Early applications include congestion forecasting and adaptive routing, with potential for task assignment and deadlock prevention. The potential for these models to revolutionize logistics is immense, but it also brings up ethical considerations. How can we ensure that these models are used responsibly, without compromising worker safety or job security? Real-world impact on operations. DeepFleet is already enhancing Amazon's network, which spans over 300 facilities worldwide, including a recent deployment in Japan. By improving robot travel efficiency, it enables faster package processing and lower costs, directly benefiting customers. Beyond efficiency, Amazon emphasizes workforce development, having upskilled over 700,000 employees since 2019 in robotics and AI-related roles. This integration creates safer jobs by offloading heavy tasks to machines. However, some critics argue that this shift towards automation could lead to job displacement. What are your thoughts on the balance between automation and human employment? Looking ahead, as Amazon continues refining DeepFleet, focusing on RC, RF, and GF variants, the technology could redefine multi-robot systems in logistics. By leveraging AI to anticipate fleet behaviors, it moves beyond reactive control, paving the way for more autonomous, scalable operations. This innovation underscores how foundation models are extending from digital realms into physical automation, potentially transforming industries reliant on coordinated robotics. But what are the long-term implications of this shift? Will it lead to a future where human oversight is minimal? Or will there always be a need for human intervention? Check out the paper and technical blog for more details. Feel free to check out our GitHub page for tutorials, codes, and notebooks. Also, feel free to follow us on Twitter, and don't forget to join our 100K plus ML subreddit and subscribe to our newsletter. Asif Razak is the CEO of MarkTech Post Media Inc. As a visionary entrepreneur and engineer, Asif is committed to harnessing the potential of artificial intelligence for social good. His most recent endeavor is the launch of an artificial intelligence media platform, MarkTech Post, which stands out for its in-depth coverage of machine learning and deep learning news that is both technically sound and easily understandable by a wide audience. The platform boasts of over 2 million monthly views, illustrating its popularity among audiences.